Hello friends, welcome back to the CSC guide. This is our third lecture of we discussing some important things in algorithm design and analysis chapter 1. So uh, in this lecture we are going to discuss a few questions. First of them is we are going to explain what is a recurrence relation with an example. First of all, what is a recurrence relation? A recurrence relation is a mathematical equation that defines a sequence of values recursively. That is, each term of the sequence is defined as a function of previous terms. It's a way to describe a problem in terms of smaller instances of the same problem. A recurrence relation typically has the following form: T of n is equals to a into T of n by b plus f of n, where T of n is the time complexity or the value of the problem of size n. A is a constant that represents the number of recursive calls. B is a constant that represents the reduction in problem size. F of n is a function that represents the work done outside the recursive calls. Now let us consider the problem of finding the nth Fibonacci number denoted as f of n. The Fibonacci sequence is defined as f of n is equal to f of n minus 1 plus f of n minus 2. Recurrence relation of the Fibonacci problem is T of n is equals to T of n minus 1 plus T of n minus 2 plus big O of 1, where T of n is the time complexity of calculating f of n. T of n minus 1 is the time complexity of calculating f of n minus 1. T of n minus 2 is the time complexity of calculating f of n minus 2. And at the last, big O of 1 represents the constant time required to add the results of the recursive calls. Now let us break it down. The problem of calculating f of n is broken down into two smaller instances: calculating f of n minus 1 and f of n minus 2. The time complexity of calculating f of n is the sum of time complexities of calculating f of n minus 1 and f of n minus 2, plus a constant amount of time is required to add the results. The problem size is reduced by 1 and 2 respectively in the recursive calls. Now let us to solve this recurrence we can use various techniques such as substitution method, where plug in values of n and simplify the equation is done. Next is master theorem. It is a general method for solving recurrences of the form T of n is equal to a into T of n by b plus f of n. Next is recursion tree method, in which we visualize the recursive calls as a tree and calculate the time complexity. Now, using the master theorem, we can solve the recurrence as T of n is equal to big O of 2n. This means that the time complexity of calculating the nth Fibonacci number grows exponentially with n. Now what is the let's calculate the fifth Fibonacci number using the recurrence relation. F of 5 is equal to f of 4 plus f of 3, which is again equal to f of 4 can be divided as f of 3 plus f of 2, and f of 3 can be divided as f of 2 plus f of 1. Then we keep on dividing it, then at the last what we get? F of 1 plus f of 0 plus f of 1 plus f of 1 plus f of 0 plus f of 1 plus f of 0 plus f of 1, which will be equal to 5. The recurrence relation breaks down the problem of calculating f of 5 into smaller instances of calculating f of 4, f of 3, f of 2 and f of 1 until it reaches the best case of f of 0 equal to 0 and f of 1 equal to 1. The final result is obtained by adding the results of the recursive calls. Next, let us explain recursive algorithm. What is a recursive algorithm? A recursive algorithm is a procedure that solves a problem by breaking it down into smaller instances of the same problem. It is a procedure uh, which are then solved recursively until the solution of the original problem is found. A recursive algorithm typically has the following structure: base case and a recursive case. In a base case, a trivial case, what is a base case? It is a trivial case that can be solved directly, which serves as a stopping point for the recursion. Next is recursive case, a case that breaks down the problem into smaller instances, which are then solved recursively. Now, let's consider the problem of calculating the factorial of a given integer n, which is denoted as n factorial. This is a Python code in which we have an if else and we are recursively doing the thing, recursively returning it. How it works: if n is 0, the function returns 1, which is the base case. If n is greater than 0, the function calls itself with n minus 1 as an argument, which breaks down the problem into a smaller instance. The result of the recursive call is multiplied by n to obtain the final result. Now we will let's calculate the factorial of 4 using the recursive algorithm. Factorial of 4 is equal to 4 into factorial of 3, which is equal to 4 into 3 into factorial of 2, which is equal to 4 into 3 into 2 into factorial of 1, which is again equal to 4 into 3 into 2 into 1 into factorial of 0. So after multiplying all this, we get 24. The recursive algorithm breaks down the problem of calculating 4 factorial into smaller instances of calculating 3 factorial, 2 factorial, 1 factorial and 0 factorial until it reaches the base case of 0 factorial. The final result is obtained by multiplying the results of the recursive calls. Now, what are the key characteristics in this? First is recursion, second is base case, third is recursive case. Recursion, it is the function calls itself. It is nothing but the function calls itself with a smaller input. Next, base case, a trivial case that can be solved directly, which stops the recursion. Next, recursive case, a case that breaks down the problem into smaller instances, which are then solved recursively. Now let us see some advantages. Recursive algorithms can be elegant and easy to understand. They can be used to solve problems with a recursive structure. Now, what are disadvantages? Recursive algorithms can be slow and inefficient, especially for large inputs. They can cause stack overflows if the recursion is too deep. Now, when to use this recursive algorithms? When the problem has a recursive structure. Next, when the problem can be broken down into smaller instances of the same problem. Next, when the solution can be composed from the solutions of the smaller instances. Next, let us discuss an algorithm for matrix multiplication of orders m cross n and n cross p and obtain a runtimes for n is equal to 1, 10, 20, 30 and 100. Now let us see this. Let us take two matrices A and B, where A is of order m and B is of order n. A is of order m cross n and B is of order n cross p, and the algorithm for matrix multiplication will be as follows. Here is the Python code and I am going to explain the algorithm. First, we create a result matrix of matrix C of order m cross p. Then After that, using a for loop, we iterate over each element of the result matrix. After that, we initialize the element c of I or of j to 0 in the inner loop. After that, we iterate over each element of the common dimensions n. After that, we multiply the elements of a and b and add to c of I or j. So this is the algorithm. Now let us calculate time complexity. The time complexity of the matrix multiplication algorithm is big O of m cross n cross p, where m, n and p are the dimensions of the matrices. Run times for different values of n. Assuming that the operations addition and multiplication take constant time, the run times for different values of n will be as follows. First case was n is equal to 1, and this time complexity will be big O of m cross p. Runtime approximately 1 unit of time, since n is very small. After that, second case was n is equal to 10. Here time complexity will be big O of 10 into m into p, because n is 10. Runtime will be approximately 10 units of time. Next case was n is equals to 20. Here time complexity will be big O of 20 mp and runtime will be approximately 40 units of time. Next case is n is equals to 30. Here time complexity will be big O of 30 into m into p and runtime will be approximately 90 units of time. Next is n is equals to 100. Here time complexity will be 100 into m into p and runtime will be approximately 1000 units of time. Note that these runtimes are approximate and assume that the operations take constant time. In practice, the actual runtimes may vary depending on the specific implementation, hardware and other factors. The runtimes are calculated assuming that the matrices A and B are dense, that is, most of their elements are non-zero. If the matrices are sparse, the runtimes may be significantly different. Next, we are going to compare the functions n square and 2n by 4 for various values of n and plot it. And we are going to determine when the second becomes larger than the first. Now here is a table which shows how n square and 2n by 4 is changing. We have calculated this table contains 20 values. We can see the table. For n is equals to 1, n square is 1 and 2n by 4 is 2 power n by 4 is 0.5. In the same way, the n square increases in the order 1, 4, 9, 16, so on till 361, 400. This is the way n square increases. After that, 2n by 4. 2n by 4, first it is a decimal 0.5, 2, 4, 8. It was increasing slowly, but after some time it increases very fastly in an exponential way. So when we use so here is a plot which shows how n square and 2n by 4 is changing for 20 for n is equals to 0 to 20. The plot shows that 2n by 4 grows much faster than n square as n increases. The two functions intersect at around n is equals to 4 and 2n by 4 becomes larger than n square for n greater than 4. When does 2n by 4 become larger than n square? This is a question. To find the exact value of n, where 2n by 4 becomes larger than n square, we can set up the equation 2n by 4 is equals to n square. Solving for n, we get 2n is equals to 4n, 2 power n is equals to 4n square, which will become n square is equals to 2 power n by 2. Using numerical methods, we find that n is equals to 4.15. Therefore, 2n by 4 becomes larger than n square for n greater than 4.5. In conclusion, the function 2 power n by 4 grows much faster than n square as n increases and becomes larger than n square for n greater than 4.5. Next, we are going to discuss Euclidean algorithm for GCD of m comma n. Now let us see an implementation of Euclidean algorithm for computing the greatest common divisor of two integers m and n. In this, we have a function GCD of which has arguments m and n, and in this we have a while loop whose condition is n not equal to 0, and at the last we return m. So let us explain how the algorithm works. The algorithm takes two integers m and n as input. The loop continues until n becomes 0. In each iteration, the algorithm calculates the remainder of m divided by n using the modulo operator m mod n. The values m and n are swapped so that m becomes the previous value of n and n becomes the remainder. The loop repeats until n becomes 0. The final value of m is the GCD of the original m and n. Let us take an example of 12 and 14. In this, the GCD of 12 and 15 we get 12 and 15 we will take 12 and 15 GCD we will get 3. Next, what is the time complexity of Euclidean algorithm? It is big O of log of minimum of m comma n, where m and n are the input integers. This is because the algorithm reduces the size of the input integers by at least half in each iteration until the GCD is found. Next, space complexity. The space complexity of the Euclidean algorithm is big O of 1. Since only a few variables are used to store the intermediate results,